Welcome to Lecture 9. Today we will explore a powerful and fundamental tool for text processing and programming, regular expressions. Often abbreviated as regex or regexp, regular expressions provide a concise and flexible language for describing patterns within strings. They are used for searching, matching, and extracting textual data, and are an essential skill for tasks ranging from data validation to log file analysis and text parsing. While their syntax can appear cryptic at first, mastering regular expressions will greatly enhance your ability to work with text efficiently. Formally, a regular expression is a sequence of characters that defines a search pattern. This pattern is written in a formal declarative language that is interpreted by a regular expression processor. The concept originated in theoretical computer science and formal language theory, but its practical applications are vast. According to the common definition, a regex provides a concise and flexible means for matching strings of text, such as particular characters, words, or patterns of characters. It is a language within a language dedicated solely to the description of text patterns. It is important to acknowledge two aspects of regular expressions. First, they are extremely powerful for text manipulation. Second, their syntax can be quite cryptic to the uninitiated. However, once you understand the basic principles and the set of special marker characters, they become not only manageable but also enjoyable to use. Think of regular expressions as a compact, old-school programming language for characters. You are programming with a very specific goal to declare what a piece of text should look like, rather than writing step-by-step instructions to find it. Let us introduce the core vocabulary of regular expressions. These are the special characters that carry meaning. The caret symbol matches the beginning of a line. The $sign, $, matches the end of a line. The dot matches any single character. The sequence HS matches any whitespace character like a space or tab, while RS matches any non-whitespace character. The asterisk means repeat the previous character 0 or more times. Adding a question mark after it, as in phi, makes it non-greedy, a concept we will explain shortly. Similarly, the +sign plus means repeat the previous character 1 or more times, and plus is its non-greedy counterpart. Square brackets define a character set. For example, AAU matches any single vowel. If the first character inside the brackets is a carré, like XYZ, it matches any single character not in the set. You can specify ranges, such as A0, 9. Finally, parentheses are used to mark groups for extraction. They indicate which part of the matched pattern you want to pull out and save separately. To use regular expressions in Python, you must first import the built-in re-module. This module contains all the necessary functions. The most basic function is re.search. It is analogous to the string method find, but instead of looking for a simple substring, it checks if a string matches a given regular expression pattern. It returns a match object if a match is found or none otherwise. A more powerful function is reFindAll. This function extracts all non-overlapping substrings that match the pattern and returns them as a list. It is like combining the find method with string slicing, but operating based on a complex pattern rather than fixed positions. Consider a simple task, reading a file and printing every line that contains the substring from. Using standard string methods, you would use a loop and the find method. With regular expressions, you can accomplish the same task using re.search. The pattern you provide is simply the literal string from. The re.search function scans the line and returns a match object if from is present. This example shows that for simple literal matches, regular expressions offer no immediate advantage over string methods. Their power lies in their ability to generalize. Now let's refine the task. Suppose we only want lines that start with from. Using string methods, we would use line.starts with from. To do this with a regular expression, we use the special carré character. The pattern from means match the string from only if it is found at the very beginning of the line. This is our first example of fine-tuning a match by adding special meta characters to a literal string. The carré anchors the pattern to the start of the line. The real flexibility begins with wildcard characters. The dot is a wildcard that matches any single character. For example, the pattern X would match XA, X, or X. If we combine the dot with the asterisk, meaning 0 or more of any character, we get a very broad pattern. The pattern X would match a line that starts with X, is followed by any sequence of characters of any length, and ends with a colon. This pattern would successfully match various header lines in an email, such as XSEV or XD spam confidence. However, a pattern like X might be too broad. What if a line starts with X but contains multiple colons, like a casual sentence, X plane is behind schedule, 2 weeks? Our pattern would still match, but it might not be the data we intend to capture. To be more precise, we can narrow the pattern. Instead of matching any character, we can match any non-whitespace character using rt_s. The pattern XRS+ means start of line literal X, then one or more non-whitespace characters, then a colon. This pattern would match XSEV and XD spam result, but would likely exclude the sentence about the plane because of the space before the colon. This demonstrates how you can adjust regex patterns to the cleanliness and structure of your specific data. While red search tells us if a pattern exists, refindall is used to extract the matching text itself. It returns a list of all matches. Consider the string. My 2 favorite numbers are 19 and 42. If we want to extract all numbers, we can use the pattern 0, 9+. The 0, 9 defines a set containing all digits. The plus means one or more of these digits. When we apply re.findall with this pattern, it returns the list to 19, 42. If a pattern does not match anything, re.findall returns an empty list. This is extremely useful for data extraction. A critical behavior to understand is that the repetition operators EET and plus are greedy by default. They will match the longest possible substring that satisfies the pattern. Consider the string from. Using the get a character and the pattern egg f per plus. This means start of line and f, then one or more of any character, then a colon. The greedy per plus will consume as much as possible, resulting in the match from using the. This might not be what we wanted if we were just looking for from. To counteract greediness, we can use the non-greedy qualifiers and plus. These match the shortest possible substring that satisfies the pattern. Using the same string with the pattern f+, the non-greedy plus will stop at the first colon it finds. This yields the desired match. From. Understanding when to use greedy versus non-greedy matching is key to writing precise regular expressions. Often we want to match a broad pattern but only extract a specific part of it. Parentheses allow us to define capture groups. For example, from an email header line, we might want to extract just the email address. The pattern Nines plus ES plus matches a non-white space sequence, followed by an E, followed by another non-white space sequence. This works. But if the line starts with from, we can be more specific. Dot from and S plus S plus. This pattern matches lines starting with from and then captures the email address part into a group. The re.findall function will now return only the content within the parentheses, the email address. To appreciate the power of regex, let's see how we might extract the domain from an email address using standard string methods. We would find the position of the E symbol with find, then find the next space, and finally slice the string between those positions. This requires multiple steps, variable assignments, and is brittle if the data format changes slightly. A common, slightly more robust technique without regex is the double split. First, split the entire line by white space to get words. The email address is likely the second word. Then, split that email word on the AYUN symbol to get the user and the domain. This is more readable than manual indexing but still involves multiple operations and assumptions about the structure. Now let's accomplish the same task, extracting the domain using a single regular expression. The pattern is elegant and direct. Let's break it down. It looks for an AB symbol. The parentheses mean extract what matches inside here. Inside we have Saya, the brackets poko, mean match any character that is not a space. The asterisk means 0 or more of these. So the entire pattern means find an is, then extract the sequence of 0 or more non-space characters that follow it. This yields the domain uct.ac.z. We can make it even more precise and robust. The pattern from Parapapu Bakais adds context. Start of line literal from, then any number of characters up to an E sign, then extract the following non-space characters. This ensures we only extract from lines that begin with from, reducing false matches.